Hi Zara, this is Alex, and I'm with Kelsey here, and we will be doing our hydrogen presentation for the use of hydrogen as a clean energy. Hydrogen is the most abundant atom in the universe. It's found in water and in many other molecules like hydrocarbons, which make up all organic compounds. It is the simplest element with one proton and one electron, and it occurs at a diatomic gas, which means that two hydrogen atoms form a covalent bond with each other. It does not occur naturally on Earth as a hydrogen gas purely, except in rare cases where bacteria produce it using the sun energy. It was first made in the mid 1600s through chemical reactions where a salt was added to hydrochloric acid, and the salt combined with the chlorine ion and hydrogen gas came off. Currently, 95% is made from steam reformation of natural gas, which is primarily CH4 methane. This process also produces carbon monoxide and carbon dioxide, and it uses a lot of heat, so it is not energy efficient. Another process depicted by the picture on the right is called electrolysis, and it produces hydrogen gas by applying an electrical current to water and splitting the hydrogen and oxygen atoms. Renewable energy is not constant, it's very variable, and say solar is produced mostly in the day, but it could supply the energy needed to use electrolysis to produce mass amounts of hydrogen gas. Hydrogen gas is much easier to store and transport. That is, it is easier to store and transport than electricity. The main use of hydrogen gas as energy is through the use of fuel cells. Fuel cells take hydrogen gas and they produce water vapor and heat, as well as an electrical current. Fuel cells work much like a battery. They produce chemical electricity to electrical electricity, and they operate very quietly. The heat and electricity produced by a fuel cell can be used in buildings or vehicles, and there are many different kinds of fuel cells, differing mostly between which electrolyte they use to allow hydrogen ions to pass through, and the operating temperatures and power outputs of the different kinds. A fuel cell produces a small amount of DC current, and an inverter can convert that DC current to AC at a low voltage. But because it is such a small amount, you need a stack of fuel cells for most purposes.
So advantages, it's 60 to 40% efficient and around 3 times the efficiency of traditional combustion technologies, which only uses about 35% of the energy. Because of its simplicity, hydrogen is the most abundant element in the universe, therefore it is an unlimited energy reserve. While it's a bit of a process for its compounds to be broken down and separated, the amount available to us makes up for this process. Its fuel cell powered vehicles would only be emitting warm air and water vapor, and there's various technology uses. It can be converted to also produce water, heat, and electricity for buildings and electrical power sources for vehicles. The main challenges associated with storage systems are for automobiles and the ability to have sufficient storage for a conventional driving range of around 500 kilometers. Even when compressed, it would require a tank taking up 4 to 5 times the space of a gas tank for the same range of mileage. Hydrogen is also extremely flammable, even in small concentrations. It is easily ignited by heat and open flame or sparks, and they can be tough to detect at first because they burn with a clear flame, and it spreads along the ground because of its density. Emissions depend on the source of the hydrogen, since typically hydrogen is made from converting natural gas to hydrogen and carbon dioxide, which is why we'd like to promote hydrogen production primarily from solar or wind power for electrolysis. However, if the CO2 emissions can be released into a point source rather than distributed, then carbon capture and storage becomes a possibility, but at another additional cost to the production phase. And lastly, it's expensive. Hydrogen produced by steam reforming costs approximately 3 times the cost of natural gas per unit of energy produced. And transportation via pipelines is costly for reasons like it accelerates the cracks in the steel, which increases maintenance costs, leakage rates, material costs, and of course the investments on infrastructure, which we'll touch on in the next few slides. Hydrogen has one of the highest energy density values per mass. For every kilogram of mass of hydrogen, it has an energy value of between 120 and 142 megajoules. 1 kilogram of hydrogen is equal to 1 gallon of gasoline equivalent. It takes more energy to produce hydrogen by separating it from other elements and molecules than the hydrogen provides when it's converted to useful energy. However, hydrogen is useful as an energy source and fuel because it has a high energy content per unit of weight. And here are specific energy values in comparison to other fuel sources. You can see hydrogen's at the 140 kilojoules mark and gasoline there in black.
Historically, hydrogen has been used in almost every type of small engine. It's also been used in buses, boats, planes, trains, motorcycles, and even rockets. Hydrogen gas has been used to fuel rockets made by NASA for a long time. And as we already said, a fuel cell produces water vapor and heat, and astronauts actually drank the water that was produced by the fuel cell. The first car that was commercially available came out in 2015, and it was the Toyota Mirai. After that, many other car manufacturers followed in suit, making attempts with car models, including Hyundai, Honda, Nissan, Ford, Mercedes, and Chevrolet. Hydrogen research has fluctuated with gas prices, as when fossil fuels are cheap, no one wants to put money into researching new fuels. And historically, research has also fluctuated with times of war, as with most other technologies. Vancouver actually had a hydrogen bus fleet, started during the Winter Olympics in 2010, but this program ended in 2015 due to high expenses, as there are no hydrogen fueling stations in Vancouver, and the hydrogen had to be trucked on diesel-powered trucks from Quebec. Currently, hydrogen is in use in many parts of the world. This year, Germany introduced their first hydrogen train to replace a diesel train stretch where electricity couldn't be used, and they have intentions to introduce 14 more of these trains by 2021 and fueling stations, as well as 60 total eventually. Currently, there are 3 to 5 car models that are available depending where you live, and they get 400 to 600 kilometers on a gas tank, or a tank of hydrogen, which is pretty comparable to a tank of gas in the average car. In Europe, there are multiple countries that have hydrogen bus trials underway, including Scotland and Germany, and many other countries are expected to follow in suit. There are also currently fueling stations in the USA, primarily in California, and in Japan and Korea. The future of hydrogen. So the Commonwealth Scientific and Industrial Research Organization in Australia has come out with an innovative new technology, which is basically a membrane combined with a catalyst that decomposes liquid ammonia into nitrogen gas and pure hydrogen gas. So nitrogen gas, as you probably know, makes up 78% of our atmosphere, and it is not considered a greenhouse gas. And hydrogen gas is the energy we're looking for. Liquid ammonia is more dense per volume in hydrogen than liquid hydrogen. This is because of the way that the molecules of liquid ammonia stack. Liquid ammonia has a boiling point of negative 33 degrees Celsius, whereas liquid hydrogen has a boiling point of negative 253 degrees Celsius. So it requires much less energy to compress and condense and is much easier to transport. This membrane has been used on the Toyota Mirai to produce locally produced hydrogen, and it has also been used in the Hyundai Nexo, another hydrogen fuel cell vehicle. This is a great technology as renewable energies that are very variable, such as solar, which is very common in Australia and has a high productivity, can be used to produce liquid ammonia through electrolysis, much like the electrolysis of water into hydrogen gas. And that ammonia can be shipped around the world to places that have a demand for hydrogen power. Other countries have invested money and are planning to invest more money and time into the development of hydrogen infrastructure and technology, namely Japan, Korea, China, Germany, Norway, and the USA.
So for infrastructure requirements, we would need to focus on sources. So we need fueling stations and engine conversions or new vehicles. Through the transition phase, we'd use existing fueling stations and put a hydrogen fueling station on site, or more ideally, we'd put hydrogen fueling sites with other clean energy fueling stations. And the opportunities are wind and solar generation of hydrogen on the fueling site. Also, infrastructure includes the pipelines, trucks, storage facilities, compressors, and dispensers involved in the process of delivering fuel. Some of the infrastructure is already in place because hydrogen has long been used in industrial applications, but it's not sufficient to support widespread consumer use of hydrogen as an energy carrier just yet. Currently, there's one public hydrogen fueling station operating in the province, which is pictured here, the PowerTech Labs fueling station in Surrey. For cost-competitive transportation, a key driver for energy independence is that hydrogen must be comparable to the conventional fuels and technologies on a per-mile basis. In order for fuel cell electric vehicles to be competitive, the total untaxed, delivered, and dispensed cost of the hydrogen needs to be less than 4 gasoline gallon equivalents, which is the amount of fuel that has the same amount of energy as a gallon of gasoline. So average cost of stations. This is a representation of the cost of fueling stations for 3 methods of delivery: gas, liquid, and on-site production. Shows the average amounts of storage for each in kilograms per day and their estimated total costs in US dollars, which includes equipment, design, construction, and commissioning. And these are US stats retrieved from the California Fuel Cell Partnership, which also offers an interactive map for finding fueling stations across the states. So how much hydrogen would we need per amount of compatible vehicles? So we see 2018 at the bottom here, hydrogen needed on the left, and total hydrogen vehicles on the right by 2030. This graph was used in a presentation for grid-based renewables and integrating hydrogen. In conclusion, there are incredible benefits for hydrogen as a fuel source. There can be 0 harmful emissions with the appropriate production process, a benefit to our planet. There is limitless supply, low user costs, and employment opportunities in the industry as well as for fueling other industries. However, without the infrastructure, the automotive industry won't push hydrogen fuel cell cars. And without consumers asking for hydrogen fuel vehicles, there's no demand for the infrastructure.
Any questions? No? All right.
Thanks for listening.